Okay. So today's topic, vector representation of semantics and the theory behind it, distributive semantics, will cover what is done in science for the last 100 years to encode the semantics of any text or word. So previously we were talking about syntaxes, about grammars, and today we speak about the meaning of words and texts and how they can be used in information retrieval. I reviewed the slides and I think that amount of information today is smaller than usual, but that means that the pace can be slower, and whatever can be hard for you, it's exactly the place for questions. So please be more interactive if it's possible. So don't hesitate. If you don't understand anything, I understand that you have very different backgrounds. Some of you are programmers, some of you are mathematicians, so some of you can suffer from web programming, and others can suffer from understanding the mathematical concepts. That's totally okay. So let's do it more friendly today. So if you don't understand anything, it's not your fault. It's just the initial position from where we start. And before we actually start discussing the real topic, I would like you to see, maybe I believe that Ikram already shared major points from here with you, but yesterday we had a pretty long discussion, an hour and a half. And here are some observations and some results which we have based on our discussion. So first of all, the major complaint from students, like some aggregated complaint, I don't know persons, I don't know how many of you, but it was major bullet which she highlighted, was that there's a very big workload in the course. And even Professor Han mentioned that whenever he meets his students, they say that they are doing homework in information retrieval. So I'm super pleased with this, meaning that you pay attention to the course. But we were trying to understand what is wrong with the course. Is it because of the course organization, our own assumptions, estimations, your misunderstanding, my misunderstanding, and what we actually found out that in this university, we have the entrance filter, which requires you to both show programming skills and mathematical skills. Okay, and you all passed this threshold. So you show that you can code and you can do some mathematics. Also, you showed that you had a semester of programming. So previously, you had a semester of doing some OOP in Java and C++ and so on. So you know how to write the code and to solve problems using programming. But still, this is not enough to be what I can call, how to say it, a confident programmer. So if you know the tool, it doesn't mean that you're confident in using. It doesn't mean that you don't know the syntax of the language or you don't know the libraries. It means that there is a pattern in your behavior that for an experienced programmer takes less time to do some task rather than for unexperienced. So for example, some of you know how to filter out unnecessary things in Stack Overflow, in documentation, and go exactly to essential parts. Some of you don't know how to do this, and you spend hours in just crawling internet trying to understand what's going on. And this is, I can address to my high expectations about your coding experience. So you meant to know some things related to web coding, about HTML and so on, but this is not the commonplace for this particular auditory. Some of you can, some of you never complain on this. You just do the homework and submit it. For some of you, this is like a problem, and I definitely need to pay attention to this because this is not doesn't mean that you cannot solve the problem, and this is very important. So actually, the master level requires you a lot of self-studying. That's normal for bachelors. You explain more, you require less. For master, you require more, you explain less, and you do self-studying. For PhD level, you explain nothing, just do science, and in 4 years graduate as PhD. That's what usually happens. Still, we have estimations, which are formally encoded in credits, which you assign to each course. And this course, as we yesterday counted with Ikram, requires around 12 hours per week of your self-studying, doing something outside the class. So we spend 6 hours or even more, 9 hours together. Yeah, so 3 hours at the lecture, 6 hours, 6 hours at lecture, 6 hours at labs, and 12 hours, around 12 hours remaining for your self-studying. But maybe some of you spend more. That's the problem. And the major part of this time is not on actually like essence of the course. It's on crawling the web, searching, and doing Stack Overflow research. And actually, it doesn't mean that the whole course is organized like this. It's not the problem of the course organization. It's the problem of particular parts of the course. Actually, web programming, HTML, and using Selenium. And all the complaints, all the requests, all the examples which Ikram provided were about doing something with web. Whenever you need to implement some idea from scratch, take the formula and implement it, or take I know the concept, which is theoretically simple, and then put it into the code, you're totally okay. But when it comes to download the page, find these blocks and HTML and these CSS selectors, then some of you are lost. Okay, and that should be considered in future. I believe that in this course, we'll try not to meet such situations again. But what can be done, and I will discuss it in the next block, I can help you with these topics even more. So what about the labs and homeworks? You said that we like not I don't know whether were you all here in this cohort, but there was an idea that you want to focus on implementation in labs. That means that you will prefer if we show you some examples of doing things which will be required in the homework in the lab. So if it's possible to show you how to solve a smaller version of the problem, you will appreciate this. And in the second place, even like if we don't need this, or if we don't require this actual, so if it's not required for the lab, you will prefer self-coding to a continuation of theory explanation. You'll prefer to have this time, like an hour and a half of the lab, for implementation of your homework because you lack of time in your homework. So that was our observation, and we will try to shift this. Like you actually started doing this in the previous lab, and we will try to keep this as is. So my only suggestion to you, so not only actions should be taken from my side, there are also actions that should be taken from your side, that a lab is the place where you try to do something. So lecture is the place where you listen for something and ask questions. So here we share a theory. In lab, you try to work with practice. And I want you to be more active in terms of requesting something. That's the idea. So imagine that there is the big file with some tasks. You go through the file, and this student and these students will have different misunderstandings. So you will suffer with web programming, you will suffer with mathematical concepts. And that means that we cannot take the common base for all of you. The common base of you is the first year of your school. So you know how to add numbers and subtract numbers. We don't know what is shared. And that means that we cannot just put the threshold very low. What we can do, we can ask you to be proactive and request for knowledge which you don't have to fulfill the homework. So if you, particularly you, suffer from not knowing some mathematical concept, raise your hand, ask Anastasia, and she will gladly help you how this works. Maybe in some simple example, maybe in some repetition, that's good. If you don't know how to approach the programming thing, we will point you in some places where you can extend your knowledge. What is requested also is that if it's possible, and if there is something which requires complex coding, using some libraries which you don't know, we will try to share with you additional materials in some form. You requested for pre-recorded videos for labs. I say that there are multiple other ways of doing this. The same explanations can be found in YouTube. There can be articles, there can be like tutorials and so on. So I will try, if I think this is possible, to share with you additional materials on exactly hands-on skills. What I also requested, Ikram, if you open GitHub repository, you will see that there is actually the list of last year homeworks. And the topics will be the same. So there are like 6 more tasks remaining. So today is the 4th homework, 3 homeworks left. Each of them will take 2 topics. They will be a combination of these tasks with some squeezing and removal of some blocks, maybe some changes. But topics themselves are taken from the previous homeworks. That means that you can briefly go through them. And if you think that something requires additional explanation, you can report it to me, to Ikram, and I will pay more attention in explaining these things before your future homeworks. You understand this? Okay. Grading. So you said that you are disturbed by grading. So you are afraid of grading, you particularly.
I said only in first class.
Yeah, but I remember you said it verbally. I don't know who said it.
I've said it even before assignments. Like you
But there are still other students complaining on the fact that the grading is taking their brain energy, and they cannot sleep and they cannot do the homework. They only think about how to get B in this course. And it sounds like getting B is a very complex task. And that's what we decided. And I will think that I will tune somehow the complexity of the homeworks, that each homework will bring you 10 plus 2 points. So it means that starting from homework 3, you remember there are like bonus blocks. This homework and next homeworks will give you 10 plus 2, meaning that you can cover one skipped homework with these additional points, or you can cover some contests which you miss. So you can get up to 10 additional points. So all in all, the course now allows you to get 115 points in total, like in the big number. So I think this is enough to be more or less confident that at least getting 70 is achievable. Okay, so I believe. So for this week, and I just specifically mentioned, there will be a block on repeating the operations from homework doing PCA on texts. So repeating the same methods. It will be a combination of what you will do in your contest and what you did in your homework, and studying classifier accuracy based on the settings of neural network. So these 2 blocks will be additional. They can bring you up to 2 points. And for the deadlines, the most important thing, there was a particular request, a single request about the next week. I heard that you have some kind of deadline in presenting of something, and we agree that deadlines should not overlap. This is an important thing, and we actually did a study and we observed that overlapping of deadlines significantly drop performance of students on the course that they think is not that important. So the first year students, bachelors, they just minus point, from A to B, from B to C. That I have a paper on this. And for next week, your deadline will be extended to Wednesday morning. So it means that you will need to submit the homework before the beginning of the lecture, because we don't want you to overlap the labs. So you solve the previous one and you can start the next one. So you can end at 9 a.m. next Wednesday. So you will get additional Tuesday. You will get additional morning of Wednesday if you can get up early. But still you have some extension. Please use it wisely. And the second thing is about the fact that you asked for extension of the deadline in general. And there are 3 more homeworks, 5, 6, 7, which require extension, maybe require extension. And this was a question for you. So from my side, I think that the deadline which is given now is fair. So I think you have enough time. You misuse it because one of the comments was that we cannot think about the lab, cannot think about the homework before we pass the contest. So first we pass the contest at 12 on Thursday, and only then on Friday we can start thinking about the homework. That's strange because you're given the homework on Wednesday, and even before you can find the statement, so you can start thinking about the homework even earlier. But this is your concern. So you have not enough time. but you should understand what will be the consequence of this change. So I'm not taking any decision. So I asked Ikram to collect some feedback. If she has the decision, she can share. But still, I want you to understand what will be the outcome. So for now, when you have a deadline on Monday, Anastasia is able to grade your homeworks before her lab. That means that she can present the feedback on your lab and your personal feedback to Moodle, and you can fix your problems and fix your behavior, fix your implementations in the next homework with respect to these comments, because this is an iterative process. For now, her timetable doesn't allow her to grade like compactly in the second part of the week. So she can do it like Monday evening and Tuesday. If we shift the deadline, her grading will fall onto Friday and weekend. That means that what we can guarantee that the grades will appear by the end of the week. That means that you will not get any feedback, not personal, not common, in the next lab. You cannot integrate it into your homework. And that means that you will have 2 weeks delay of sharing the feedback, and it will overlap with the lab. So you will do one lab and you will get the feedback on the other lab. So it can decrease the quality of feedback for you. So because we cannot drop the quality of feedback itself, so we cannot say that we will not do any feedback. We just give you grades and go there. So it will not be very pedagogical. And so that's why I want you to decide whether you prefer to stay with this deadline, knowing that we will increase the points and we negotiated on improving everything related to complexity. So adding some examples if it's needed, making the size of the homework comparable to this one, the fourth one. So if you look at the homework, Ikram said that this one looks like feasible. It's possible to do it without any extension. So if you think that all these measures are enough, we can keep this strategy as is. So starting from the homework 5, 6, and 7, we will return to the Monday deadlines. If you think that you don't want this, if you want just extension of time and don't care about feedback speed, we can extend the deadline. So there's no significant problem from our side. The only is like you are affected by your decision. So Nastya will grade in other days. So that's general observations. And I think I will give you a chance to think about what you prefer in terms of deadline. And after this first lecture, we'll maybe make a poll, or if Ikram has her feedback, she can share.
Can I share? Actually, I shared on the text in Zoom. Only 4 people didn't vote, but I don't know if you can read the messages. 4 people voted for Tuesday.
I will.
6 people for Monday.
Okay, I'll open the chat. 4 people Tuesday, 6 people Monday, 1 voted both, 5 didn't vote. Okay, so that means that majority prefers to keep the deadline. That's democracy. Sorry, guys. This will take 6 hours of grading from Anastasia. So this should be discussed with her, not with me. I'm only a provider here. So this negotiation should be done with Anastasia. I was just, Ikram shared with me the feedback. I shared it with Anastasia. She showed me what will be the consequences. So you now decide. And I prefer you at the lab today discuss possible extensions. So for now, we keep the idea that majority prefer 6 p.m. Monday, but maybe you will negotiate some things with Anastasia today. Okay, maybe 8, maybe 9. I don't know what she can give you, what will be the present from her side. Okay, so are we done here? Any other feedback? Any other?
I wanted to ask you something. You just said it earlier, but I didn't got you. You said that if the deadline will be Monday, the length of the homework will be shortened, like the homework number 4, right?
This is not the the consequence and the cause. This is just we discussed that the homework for now is big. And I showed Ikram the 4th homework, and she says that this one looks okay. And I will try to keep this in the same size for the future 3 homeworks. It doesn't mean that one means another. It means that I will do one and you decide on the length of the submission deadline.
So the conclusion is you will reduce the length of the homework for
Not
the future
reducing it.
ones.
So the 4th one was designed before this discussion, and now it looks like okay. So I will try to design next homeworks in the way that they are comparable to the 4th one.
Okay.
Because
And
they're not
if the deadline, if the deadline will be Tuesday, then you will not reduce the length of the homework. They will be like the previous
These 2
ones.
processes are not connected. So the size of the homework is one question, the deadline is the other question.
Okay. So we prefer like to reduce the length of the homework.
Okay, I see.
Then I'm okay with Monday. I will take my vote back from Tuesday.
Okay, I see.
Thank you.
So we spent pretty much time on discussing, the question from offline.
These +2 marks, it will be very hard to get these +2 marks, isn't it?
I think that for this homework, if you look at the statement, that's not too hard, because actually, as I mentioned, that the first point is applying the method which you implement before to the data which you use in your contest. So you know how to take the data, you know how to use the method. If you merge these 2 things, it will be like, I don't know, 20 lines of code, which is just a combination of two blocks. For the second classifier accuracy, you have the code for training a neural network. You just prepare the classifier, and then you do some grid search of parameters and see how parameters of the classifier affect the accuracy. So that's what you did in your, I think, machine learning course.
I think you should give us labs too. Like you should help us explaining labs too.
But you have a TA for this.
But still.
But then they should pay me more.
But it will be more
You know that I'm teaching the normal workload of a professor in university, but I'm 0.7 professor here. So I need to teach one course less than others, but still I'm doing the full job. So if you ask me to teach I'm totally okay, but you should negotiate with the director of university to pay me some money more. Okay.
My the reason of asking about these +2 points that if we're having hard time getting 10 points, if you make these +2 points more harder, so it will be like near to impossible.
I will try to do these 2 points comparable. So of course, this is extra points. The extra points cannot be for free.
But it should
That-
be like less value or something.
Like, I understand the idea. So this homework was designed before and we negotiated, and I think that this 4th homework is a good step towards your expectations. For the 5th homework, I will definitely think about doing these extra points, not that hard to obtain. No problem. Whew, let's go for vector representation. Tuesday, Wednesday, doesn't make any difference. Comments from online. Perfect. So let's go. So our today's agenda for the first lecture, which remains only an hour, how to reinterpret the Boolean query which we discussed in the previous lecture as in a vector form. We'll speak about distributive semantics, and we'll speak about dimensionality reduction and the latent space analysis method. Before we start, so no initial questions, great. So just a thing which can be, and which is very important for all the future material which we'll have today. So let's speak about the thing which is called term document metrics. You remember that at the last lecture, we discussed that the text itself can be represented in a form of bag of words. So it means that we take a text, we collect all the words together, and we just store them with the frequency of their appearance. So the number of times the word appeared. So now the text is not ordered, it's a multiset. And you remember that there was another method which allowed us to express this value of the word, not with the absolute value of like numbers, but with some relative things. And this thing was called TF-IDF. where we encountered both term frequency, how term is frequent in this particular text, and inverse document frequency, how this word is distributed among all the text. Is it a common word for all the text, or it's a very good, well-specified word which appears only in 2 texts out of 1 million? So yeah, so these 2 factors can influence the number which will be attributed to the word. So for now, our representation of a single text is words together with some values. If we take the lexicon, the vocabulary of the language, and we fix it as the ordered sequence. So let's say we sort it alphabetically, so from A to Z. So all the words, let's fix this number for the future lecture, that we will have, how many? We will have, let's say, 100K of words. Yeah, so 100K of words. And then we do what? We will fix this number, sort the vocabulary, and then we will fix the documents, and we'll sort them by index. So, and we will have, let's say, 1 billion of documents. Then we can form something which is called a term document matrix, where term stands for the word from vocabulary, for lexeme, and document stands for document. So some file on your hard drive, maybe some paragraph from the text, whatever you think a document in your case. So what will be the item of search? If you search for a paragraph, it will be a paragraph. If you search for a document, it will be a document. Okay, and then this matrix, so if you have these fixed numbers, this fixed number, let's form a matrix, which will have here documents as columns, and terms as rows. And the intersection will hold these numbers. So in some cases, these numbers can be just the fact of occurrence. So there is a word like this in a document, just Boolean, yes or no. In some cases, it will be the absolute value. So how many times this word appears. So the term document matrix doesn't define it actually. It says that it should be a frequency of term in some understanding. And sometimes it can be some fractional number like obtained with TF-IDF. And also, if we transpose this matrix, so we call it document term matrix, then it's just the matrix where documents come in rows and words come in columns. So you just understand that maybe sometimes you will catch me on mixing them, but what I actually mean that this is the matrix storing connection of documents to terms, and term document matrix where words are rows, and document term matrix where words are columns. And we expect to have 1 billion of documents for like contemporary system, it's average size, and we expect to have 10 or 100,000 of different lexemes in our vocabulary. So yeah, columns now are like this, just bags of words. So this column represents a bag of words in a vector form. Rows are, again, the vector representation for a particular word. So you see that there are some numbers. It appears in some texts and doesn't appear in other texts. And if you look at a couple of words, let's say, I don't know which one to choose. I mean that some such rows can be highly correlated because the words appear together in the same text. Yeah, for example, and some can be not that highly correlated. But unfortunately, this set of words is from the same topic. That's why in this example, it's not easy to show. But here, for example, you say cat in both documents, rat in one document, and whoever is here, the dog is in the other. So rat appears in one document and rat in one, dog in the other, so they don't correlate. So there's no correlation between these terms.
But rat and cat, what is it like dog? They have relationship with.
Yeah, cat has relationship with rat and cat has relationship with dog. That's obvious. So cat hunts rats. That's why they appear in the same text. Cats don't like dogs. That's why they appear in the same text. But usually there are no connection between texts about rats and text about dogs, because they don't negotiate like just it's a simple example of how it happens. And one more important thing, that if we have this matrix, you imagine that there's a billion, there is hundreds of thousands of objects. So if you multiply, you will get what? You'll have hundreds of trillions of positions. And of course, not all the words are present in this particular text. And this means that the matrix is sparse. Yeah, so do you know the term sparse? Sparse means that the number of elements in the matrix is comparable to the dimensions of the matrix. So the number of elements is comparable to m or n. When the dense matrix means that the number is comparable to m by n. Yeah, so it's a dense matrix. You understand the difference? Okay, great. Let's move to the vector space model. So we just discussed that the text can be encoded in a matrix. So matrix is perfect because it's a very well-studied mathematical concept. Is there a way to represent the meaning of texts or the meaning of words by vectors? So sounds like we are near. So let's speak about what should be there. What should be the requirements for this kind of representation? So first, both documents and queries, what we use for search, should be represented by concept vectors. So concept is a thing which is the, let's say, unbreakable part of meaning. In the very first approximation, you can think about concepts as about terms. So you can represent a text with terms. And in your previous slide, you saw that there was a representation of documents through the terms. Yeah, but this is not exactly the match, and we will see why this is not possible to use just words to represent text. The second, the number of concepts should be pretty small, and this number of concepts should represent some high dimensional space. And the elements of these vectors in this space, so the space of vectors, the elements of this vector should correspond to weights of concepts. So one dimension of this vector means the concept, and the bigger is the number, the higher the weight of this concept in both query and document. For example, it can be TF, IDF value. And this space should be not only vector space. You should understand the difference between vector and metric space. Who can say what's the difference? Vector and metric space from mathematics. So this is very simple. Vector means the space of vectors. What does it mean? There are vectors, and you're allowed to do some operations with vectors. Yeah, which operations? You can multiply a vector by a number, by a scalar. You can sum two vectors. Yeah, and these are operations which are allowed to you. So you can do these operations with vectors, and you have no idea about the meaning of these vectors. So is there any, I don't know, sense in this summation? Is there any sense in this multiplication? Whereas the metric space says that the objects which we store in the space, they're not necessarily the vectors, but this space defines a metric. Metric, what is metric? Metric is the function which takes two objects in this space and returns a number. And it has some properties. So metric cannot be negative. Metric should satisfy the triangle inequality. So if there are three objects, and there's a distance between two objects, distance between two objects, and the distance between the first and the third one is smaller or equal than the sum of distances between these. So the metric is the function of distances, actually. That just you can, for visualization in your brain, you can use Euclidean distance. Just imagine any dimensional space, and the Euclidean distance is a good metric. And if we combine vector and metric space, we say these are vectors which has metrics. So some understanding of distance between them. And there should be a function defined for such vectors. So vector space model requires you to define such a distance. And this distance should be, for us, as for people who do information retrieval, some glance of relevance. So relevance is important. We want to use this metric to retrieve relevant documents for our query. So we will speak about relevance, and we will say that the similarity of documents in some terms, similarity in terms of semantics, will be a good approximation of relevance. If the documents are like query, they will be with a high chance relevant. If they are not like query, if they use completely different concepts, completely different words, they are not like query. So we don't like them. And we will boost the documents which are similar to the query, and we will pessimize the documents which are not like a query. And here are two concepts which are usually connected. So the similarity, so the relevance higher to 1, similarity higher to 1. And the distance actually starts from 0. So the distance between equal objects is 0. So like Euclidean distance. If 2 points occur in the same space, they are having the distance 0. Yeah, so that's why similarity and distance, they should be somehow connected, but similarity grows, distance falls. Distance grows, similarity falls. So how can we define, for such a statement, how can we define a distance for a vector space? What's your suggestions? So we don't know what are the concepts yet, but what can be the distances which you know? Cosine similarity, one of the distances. Other distances? Euclidean distance. So, and any L something distance. So Manhattan distance when you have L1 norm, L2 norm, which is Euclidean distance, L3 norm, and so on. So there are multiple different metrics actually, which can be introduced. So we will use some of them and maybe not use other. So let's look at this picture. So assume for now that words are concepts. So there are some atoms of meaning. So something unbreakable in terms of meaning. So this is educational, finance, and sport, which define our text. So, and we have these words with some frequencies, and these arrows represent some documents. What do you think? Which document here will be the closest to the query? Just in your perception of the situation. So what do you think? Which one should be returned at the first place in ranking, given the query, which is the red arrow? D1. Why?
The angle between query and D1 is small.
Okay, so both answers relate to angle. So you say that the cosine distance is smaller for D1. You say that the angle is smaller to D1. They are connected, of course. I can say that, for example, it's not obvious from here, but maybe the Euclidean distance between query and D1 and the Euclidean distance between query and D4 is almost the same. So it's comparable. Maybe for this example, there should be a more tricky example. But you in your feeling, you both decided that angle is more important here. Not the length of the vector, not the Euclidean distance, but the angle. So that's your feeling. And let's see, is it good or not. So before we start choosing the metric, let's define what's the, let's consider the following thing, that so the basic concept, the idea of concept is not defined in vector space model. So there are concepts, but we know which words should be used for concepts, how to define the concept, how to choose a concept, no particular program or algorithm to extract them. The only thing which is assumed that these concepts should be orthogonal, meaning that, like in the picture, the meaning of one should not affect the meaning of the other. So they should be separable from each other. So this text is about the sports and education, and these are not highly correlated dimensions. But as we look at the term document metrics, we can see that, for example, two word phrases like New York, like Annapolis University, like, I don't know which one, I don't know, black tea. These words often occur together. It means that if you look in the term document metrics, if you take the row corresponding to the word, what you will see? You will see highly correlated rows. So if you do measuring an angle between these two vectors, it will be very close to 0, and the cosine will be very close to 1. So that means that the words which occur in the two-word phrases, they are with a high chance non-orthogonal. There is the person who runs forward the lecture. Maybe he saw the last slides. So please don't help me. I will go there by myself. Thank you. Second thing, that we don't know how to assign weights. There is no particular procedure defined for vector space model. And that actually weight for query and for document means slightly different things. For query, it means that how important in this term, like concept in terms of this query, and for text is about characterizing the document. So first speaks about information need, second speaks about representation in terms of document. So this is very hard to bring them to the common denominator. And actually, vector space model doesn't define the actual, the only distance which we should choose. Okay, why Euclidean distance is bad in this case? So can you say, so why your choice was more about angles rather than Euclidean distance for such an example? But it was your first decision to take cosine similarity and to take the angle. Why not Euclidean distance?
This is three-dimensional space.
Three-dimensional space.
Easy to work with angles here.
Yeah, I mean the compute angles is easy in any space. So my idea is the following. So very simple. Imagine the Russian masterpiece, the Russian book called War and Peace. You know, it's one of the longest books in the world. It's not the longest one, but pretty long. You know, four volumes. And if you take any way of encoding the frequency, TF, IDF, or the absolute values, the length of this vector will be enormously long. Yeah, so because the values and dimensions are very high. And imagine a query, which will be war and peace. Okay, what will be the length of this vector? So comparable to the length of the book, pretty high. And imagine that there is actually the Wikipedia article saying about something like Leo Tolstoy, for example. And in one of the paragraphs, you will meet war and peace. So these words. Okay, and you know that Wikipedia article is much shorter than the story itself. But in terms of Euclidean distance, the Wikipedia page will be definitely closer to query because just they are both short vectors, and this one is long. Yeah. So if you search for one thing and you rely on the size of the thing, it will affect. So the shorter documents will be retrieved with a higher probability than the longer documents. So we need to somehow get rid of this bias. We don't need to be biased to short documents because of Euclidean distance. We need to somehow fight with this bias. Okay? So how can we fight with this bias? Introducing some metric which doesn't care about the length of the vector, the norm. And here comes, ta-da, cosine similarity. Cosine similarity is a projection of one vector into another, and it returns 1, so the cosine of 0, 1, when the angle is 0, so when the vectors are collinear. So in this case, if I draw the vector like this, or the vector like this, so let's call them x, y, and z. So vectors x, y, and z will have cosine similarity equals to 1, because the angle is 0 between them, no matter what's the length. Z and y and x, they all collinear. Length is not important because length goes in the lower part of this fraction. Okay, so we norm by length. And 0 means vectors are orthogonal. So the angle is 90 degrees in the dimensional space. And that means that these concepts or these vectors are orthogonal, so they don't actually share any meaning. So when one has, so let's say one is about sports, another is about finance, they don't share any common concepts. And when we speak about the distance, so we need to define a metric, not a similarity. You remember that there is the cosine distance, which is 1 minus cosine similarity. Okay, so distance is defined just 1 minus this. What about negative values of cosine? A very good question. We will speak about this a little bit later, about the fact that if you imagine the space which we speak about here, you will observe an interesting thing, that there cannot be a negative value for a frequency. That means that all the vectors will live in a two-dimensional space in this quadrant. Okay, so and then inside this quadrant there cannot be negative values of cosine. Okay, but in other cases it depends on the task, it depends on the problem. Sometimes it can be a good idea to just, because if you care about collinearity, -1 is also collinearity, but they are just looking in the different directions. Okay. So yeah, now we came to the following situation. So we have defined the metric which is good enough for taking the closest query. So this one is the closest in Euclidean distance, but we like somehow by our feeling understand that the better choice will be this one. Yeah. So these two, query and D. That means that we will remove the norm and we will keep only the essence of the document, the general direction, the general idea about the data. Okay, let's stop here. So we found at this moment the way which allows us to represent any document as a vector. So we already saw this term document matrix, and we know that the document is a column in this term document matrix. So there is a vector representation. We know, unfortunately, we know that there's the single thing which should disturb us, that the concepts are here non-orthogonal at the moment. But we introduce the relevance approximation as the simple mathematical concept, cosine similarity. And we actually see that, yeah, cosine similarity, even in this case, can work. The documents which share the words will give us the bigger cosine similarity. The documents which doesn't share the words, they don't share cosine similarity. So they give us similarity close to 0. Yeah, so this already works even if the concepts are non-orthogonal. And the technical thing here is that to measure similarity between two documents, doing a dot product, like doing a cosine similarity computation for 100 words representing the document, we will need some hundreds of thousands of arithmetical operations. So we will need pairwise multiplication and summation of all these values to run this comparison. And of course, just imagine how many you should do with 1 billion of documents. So you take a query, you run linear search, and this will be a very, very long walk. Okay. So what can we do to make the number of dimensions smaller? What can you suggest? How can we reduce dimensions? I saw PCA in the chat. What other approaches can be used? So just how can we reduce the number of dimensions? Excuse me? Regularization. What do you mean? It's like PCA, something like PCA. Okay. Actually, if we look here, there are some maybe dummy, maybe some stupid, but still working approaches. The simplest possible compression approach, which is actually used in the data structure called Bloom filter, is what is using the mode operation. So we will just fix the number of dimensions we need, and we will write information about some dimension into this place modulo max size. Yeah, that's a strange approach, but this approach works because what? Because we have a sparse vector, so there is a chance that they will collide, that the two concepts which pretend to the same place, for example, we have max size of 7 and the concept which stands on the position of 4 and the concept which stands in the position of 11 will pretend on the same place. Yeah, so they will be pretending to take the place 4 in the vector. But first of all, the chance of this is not that high. And the second, what is the consequence? So if two values jump into the same cell, it will do what? It will result in false positive matches. So the documents which don't have the concept will be retrieved for a query. But is it the worst which can happen? We will have false positives, but we can filter them out in the later stage. So for pre-retrieval, for initial stage, this can work. And this idea is actually used in the data structure called Bloom filter. If you heard about this, this is the probabilistic implementation of set. So you have a set, and instead of dedicating 1 bit for an item, so if you have a set of billion elements, you will have billion of bits. That means that 128 million of bytes. So it's 128 megabytes for storing the set. Pretty big amount of memory. What you can do, you can dedicate less memory, and you can say that each element will be represented by a hash function, which will raise few bits in this block, and then you allow different hash functions to put values in different positions and even collide sometimes. But the probability properties of that data structure show that you can balance between the size, between the number of hash functions, and you can achieve like 99% of not getting false positives by tuning some parameters. So you can have false positives, but you can significantly reduce memory usage. So Bloom filter, you can read about this, is a very beautiful data structure. Bloom, I think Bloom's filter. So it's an approach which is used in your browsers to store, I think I mentioned this in the course, to store potentially bad websites. So you have this big number of links which should be banned. And if you will go to the Google server before each request to check that this site is bad, you will put a significant load on the servers of Google. So you want a website, but instead of you go to the Google servers and then to the website. Instead of this, Google allow you to store the Bloom filter with hyperlinks, which are meant to be potentially bad. And first you check there, and if it triggers a positive result, so yes, this is a bad website, you go and recheck it in the Google, because it can be a false positive, but only in case it triggers. But if there is no such website, you can go there without any warning. So it's meant to be a good website. So one approach, compressing dimensions by just occupying the same place in the concept vector for different concepts, just they jump in the same place. Other approaches is projection of this multidimensional space into a lower dimensional space. What can be types of projection? So first of all, you can just randomly remove some dimensions, say we don't care about them. So I will find some other ways of expressing these terms, maybe in some other correlated things. And this works. Actually, if you randomly remove pretty big number of dimensions, it will still work. You will still be able to retrieve relevant documents with some, of course, loss of accuracy. And the other concept, which is very beautiful, which is called the random projections. This method is theoretically proven in the end of 90s. I will not. So I think if you click here, we will see the names of the persons. Yeah. So there is the lemma. So let's see. Yeah, Johnson, Linden, Strauss lemma, which is proven in the end of 90s. And this lemma in general states the following. It states that we can reduce the number of dimensions in some high dimensional data set without respect to the number of dimensions, but with respect to the number of items. So yeah, the idea is the following. So if you have some data set, some data, to preserve the distance, to preserve the Euclidean distance in this data set, we don't need that many dimensions. The number of dimensions should depend on the logarithm of number of items. Yeah, so we can find such an approximation with linear projections that will preserve Euclidean distance between pairs of points at this vector. So vector epsilon means what will be the size of the error, and it stands here in the denominator. But the number of dimensions is depending not on the actual number of dimensions, but on the number of items. It's a very beautiful lemma. It says that no matter how multidimensional can be the space, it is actually more important to know how many elements you have here in the data set. And this approach it found another implementation in indexing. We will speak about this implementation in the next lecture, in the next class, I think next week. But this is an approach. Yeah, so you just do some random projections, and the lemma proves that if you do random projections, so if you take a random hyperplanes, you project the points on these hyperplanes with a very high probability, you will not lose Euclidean metric. You will not have significant fluctuations in the Euclidean distance if you do this number of dimensions. So if you do logarithmically comparable number of dimensions to the number of elements, you will have this good result. So Euclidean distance will be almost preserved. Beautiful result. Still requires some computation, so you need to run this procedure. If you have a billion scale data set, you will need to project any point these dimensions. It's computationally expensive. Other approaches, we will speak about latent semantic analysis, methods like ALDA, PCA, and of course, contemporary approaches with neural networks. So finding vector representation for text data sets using some complex functions, which we don't control. We just give them the task to find these representations, and they try to do this. And we will speak about the latent semantic analysis right now, and about the networks at the next lecture today. Okay. So some people write some words like PCA, singular value decomposition. So it means that you didn't see the slides yet. Okay. So we will start with the idea, which is actually almost 100 years old. I think even more. So the idea of distributional semantics and the distributional hypothesis was stated first in 1920s. And the idea was like, it has few different interpretations. You can look here. So linguistic items with similar distributions, whatever it means, have similar meanings. So this is the hypothesis about our language. If something appears in same distribution, some fuzzy word, then this something is similar. That words that occur in the same context, better, context is more defined term, then tend to mean the similar meanings. Great. So context is much better than distribution. And the most published formulation, most published form of this hypothesis is that you shall know a word by a company it gives. Yeah, so there's a company of words, and you can fill the gap by knowing the context. Okay, so few notes about this. So similar, so yeah, do you need the example of the idea? So simple example. So let me say that there is a sentence, the big and angry blank space ran on me and crashed my car during safari in Africa. So big and angry something ran on me and crashed my car during safari in Africa. What will be in this place? So what would you suggest for this block? Elephant, okay. Any other suggestions? Man? Okay. I was not supposed to hear this, but okay. Actually, hippo and maybe giraffe. Yeah. So which animals are that big that they can actually crash the car? So elephants, hippos, and maybe elephants, but maybe something else. But the idea is that by the context, you can restore some concepts about this thing. This is a huge thing living in Africa, so you significantly reduce the scope. And this something can be angry and that big that it crashed a car. Okay, and yeah, and that means that most probably these words, they are very interconnected. And I even saw this example at my friend's home. So you know that children today are having the distant classes, and there was a class when the children were trying to study soft and hard consonants. So like in Russian we have, for example, n and n. Yeah, you see, you hear the difference. So n is hard, n is soft. Yeah, and they were doing on the example of different animal names. And in Russian we have the word sorry. I just lost. So in Russian, there's a word nosорог, meaning hippo, and the word slon, meaning the elephant. Yeah, and there was the case that the teacher just mixed these two animals, and she was trying to ask student, what is it soft or is it hard letter L in the word nosорог, where there is no such letter, and she was trying to, is it hard or soft? And the student was sitting like, there is no such letter in this word. And, oh, in the picture, it's not the elephant, it's a hippo. And that because for her, these two concepts are that such mixed in her brain that she can easily substitute one by another. So it's our brain which stores them in the very near places in the brain. So in this distributional hypothesis is trying to support this idea that sometimes we can, like my wife is always mixing cakes and I don't know how actually, what's the difference? How you call tort in English? Cake. And how you call pirog in English? The pancake, it's a blinchik. So I mean that in Russian we have different words for open and closed cakes. And my wife is usually just interchanging one word with another. So for her, these two concepts are the same. She doesn't care. So these all examples were about the idea that distributional hypothesis sometimes project in our life. So we sometimes misuse words with very similar meanings. Okay, few notes here. As I mentioned, similar context and similar distribution are not well-defined terms yet. So the hypothesis is very fuzzy because it was a hypothesis from linguists, not from computer scientists. So we cannot give a fuzzy definition and expect that something will work exactly as you defined. And this can go for different ideas in different models. In term document metrics, you do what? The context is just the bag of words in which this word occurs. So you can say the document itself is a context. If we will move to word-to-vec model, we will speak about the near context of the word, like neighboring 5-4 words in the sentence. So the context can be large enough and small enough, depending on how you use it. But still, distributional hypothesis is a very powerful model, which actually made us to happen all the topic modeling and all contemporary machine learning based NLP techniques. So it gave us an idea that distribution of words can be a good source of information. Because if you look at any NLP model today, you don't need additional markup for data. So for any machine learning task, you need what? You need data and you need target. Data and target. For NLP, you just need corpora. You just need texts. Yeah, so you don't need to read a billion of texts and put some numbers near them. Because what? Because distributional hypothesis said that what is important for a word is the neighboring, some context, maybe a sentence, maybe a paragraph, maybe a few words in the round. And that's enough to create the target for training. The consequence is that distributional hypothesis significantly improves our worries about the fact that the words which occur together, they definitely correlate. They not only correlate in terms of term document metrics, but they also share the meaning. They share the concept. Yeah, so this B words, phrases, or interchangeable words, they are very suspicious. They cannot be candidates for orthogonality because they, in both term document metrics, they fail cosine metric. In distributional hypothesis, they say what? Sorry, we occur together in the same context, so we share the meaning. But somehow we can think about inferring orthogonal vectors from term document metrics. And the guys who were sharing the ideas in the chat, you're actually right. And we will go here and see what can be done to infer orthogonal vectors from term document metrics. And the idea is, yeah, the question.
For example, if we have two sentences, in one we have like word, in the another we have pronoun.
Mm-hmm.
So which means the first word. So in this sense, we're losing the context of the first word. I mean, like we have in the second sentence is also describing the first word, but using pronoun.
So you mean the lexical role is different? The word share the same semantics, but the lexical role is different.
So context, yes, they both have the same meaning.
Mm-hmm.
So they actually should have same context. Like for one word, it will be two sentences.
And
But don't we have only one?
can you provide the example? So I mean, it's slightly lost. So what's the problem right now? So we not even came to the methods yet. So we only discussed the approaches. So there's an approach. So what's your what you worry about?
Can I say it on Russian?
You can say it in Russian. I'll translate.
То есть у нас есть два предложения.
Мгм.
Мы говорим, моя мама хорошо готовит.
Мгм.
Второму мы говорим, у нее получается это очень вкусно.
Мгм.
И получается то, что во втором мы говорим про мою маму,
Мгм.
но другим словом.
Ага.
То есть смысл один и тот же, но в нашей модели это будет как отдельное слово с отдельным.
Okay, so you worry about the fact that there are two sentences like my mother cooks well, she is preparing tasty things. Yeah, and we replace mother with she. Yeah, so we noun with a pronoun, and we lose the connection here. And yes, this can. No one said that this model is like perfect. This model can fail in some cases, but contemporary models like BERT, like transformers, they actually encounter this. They are trained to predict such relations. So like nouns and pronouns, for example, when you point to a person in the previous sentence by some pronouns in the second. The problem is with any modeling. So if you have word model somewhere in the slide, you should be aware that model doesn't mean exact projection. Model usually what? A simplification of the world just in purpose to solve some problems. We will fail. As I mentioned, like There were a few methods of doing dimensionality reduction. Any of these methods will lose something. And we will choose one of the projection methods to solve our problem. If we don't care about actual accuracy, we will maybe influence the metric. If we care about actual accuracy, maybe we'll prefer having some false positives, but keeping the metric exact. So depending on what is our need, we will prepare the model in the way it's still useful for our task. In your case, you say that we can lose some semantic connections. Yes, we can. Is it still possible to use these models for natural language processing? Yes. So yeah, these things can happen, and no one says that the problem of modeling the language is solved. You know that there is still a model like GPT-3, which is meant to be a very high result for generating natural text, but they are like meaningless. So you cannot use it for generating text actually. What you can do, you can generate something on the topic. But if you want to like force this generation to follow your idea, it's very hard. So this generation is uncontrollable, almost uncontrollable. Okay, so let's go. We have only 20 or 15 minutes left on this topic, and I think I will be able to cover the remaining things. So let's speak about how we can reduce dimensions and bring the idea of orthogonality together. So these two things will be very useful if we do it together. And here comes latent semantic analysis. The idea was patented in the late 80s, 1980s, and it is based on low rank approximation. So the actually the patent says the following: take term document metrics and do SVD on this. So we will speak about this in more details. So idea is the following. So we will think the following. So the hypothesis says that there is a latent semantic space. Latent means hidden, so unknown, some linear metric space, which the place where all the concepts live. So they are orthogonal, they are beautiful, they represent dominion. We need them, but we don't know how to obtain them. And our thing says that maybe we can take the distributional hypothesis, somehow think about it, and propose the method which will bring us to this place, to the place where concepts live. And latent semantic analysis says the following. So let's do the following. And it should work in search task. We will search for a low rank approximation. What does it mean? What is the rank of the matrix? What do you know about rank? So what's the rank? It's an amount of linearly independent vectors, where a vector can mean both rows and columns. So if we rephrase this definition, it means that the number of rows or number of words or the number of concepts which are linearly independent. Okay, so we know that there is definitely some big redundancy in this matrix. It's sparse, it has highly correlated rows. So it means that maybe there is a space of low rank, so smaller number of dimensions, which can give us the good approximation for the original matrix. So it doesn't mean that we need to have this exactly equal sign, but almost equal will be also okay. And how it looks like. So if we imagine there is the query vector in our usual lexical representation. So let's fix that. Here are some numbers. Let's fix that the number of words, you remember it was 100,000, and the number of documents is 1 billion. Okay, so what it says, we have the query vector, which is represented by a column vector, so all the words in the lexicon, and we put our words in these positions where they meant to be. Okay, so we have the query war and peace. We will raise 3 numbers in this vector, so it will be almost 0, and 3 values in the place for war, the place for end, and the place for peace will appear. Okay, that's how we form a query vector. these numbers can be also not just 1, 1, 1, but they can also be, for example, managed by document frequency. So how frequent are these words? Okay. So what should we do to obtain the closest document by a similarity? You remember, our similarity definition was what? A cosine similarity between the two vectors. Okay, you remember cosine similarity. What is cosine similarity? It's a dot product divided by norms. Perfect. Yeah. What if we say that term document matrix, in our case it will be DTM, document term matrix, so it's transposed. Yeah. What if this matrix has all the rows and also all the columns? Oh, sorry. All the rows corresponding to documents normed. So they are, before we do any operations, we divide them by norm. So they store the values of vector divided by norm. Okay. If we then do a dot product of query divided by query norm, yeah, so this is what we store in our index, and this is what we will multiply by. What we need? We need only dot product to run cosine similarity operation. Yeah. So that's why sometimes when you speak to a person who works in information retrieval, they will interchange these things, because by default in any information retrieval system, you will think about the vectors representing the text as about normed vectors. So we usually don't even think that it can be that we store non-normed vectors, because like if you think that cosine similarity is a good metric, you will definitely do all your best to take as less operations as possible during the computational phase. And this means that I don't want to compute the norm on the run. I want to pre-compute the norm, and I don't want to use it. I will use only normed vectors here, and I will use normed query vector here. And what it gives me a chance, so normed vector here, normed here, to use dot product instead of cosine similarity. So cosine again, so cosine equals vector by query divided by vector divided by query. If we pre-compute this one, vector divided by the norm, and store them in term document matrix, and if we use not query but query normed divided by a norm, what we have? We just need compute cosine similarity by dot product. Okay. Okay. What is multiplication of this matrix by a vector? It's actually applying dot product to any row with this column. Okay. Matrix by a vector is what? Dot product of the first row by this, dot product of second by this, and so on. So this operation, term document matrix multiplied by query, will return us the vector where it will have the same number as the number of documents and the dimension of 1 here. So it's just a vector where each position holds cosine similarity between the document and the query. Okay, so this is a very important concept. So this operation means that to know what's the similarity between the documents and between documents and the query, you can multiply term document matrix by the query. So the simple operation, just multiplication. And what will be in this matrix in Rankins? So I think it's a bad word I used here, but the matrix will store similarities. The higher is the value, the higher you should raise the document in ranking. Okay, the lower is the value, the smaller is cosine similarity, the further are the documents. And our suggestion is the following. So about the, you remember, low rank approximation. We say that there is a decomposition of the matrix with lower ranks of the matrix into two matrices with lower ranks. So it means that what? We have 1 billion of documents here and 100,000 words here. And we assume that it's enough to have only k dimensions. So the rank of the matrix is k, not more than k. So actually, for such a matrix, it's very hard to compute the actual rank, and most probably the rank will be big, but we need just an approximation, not exact decomposition. Yeah.
I have a question regarding ranking.
The question.
Like 3 or 4 slides ago, it was written that the cosine similarity can be true or false, 1 or 0.
Oh, it's the cosine similarity can be 1 or false in the extreme cases, and it can be any value between 0 and 1 in cases. So for two-dimensional space, these two vectors have an angle of 90 degrees. They are orthogonal, and their cosine similarity is 1. Oh, sorry, 0. Yeah. For these two vectors, for A and B, the angle is 0. The cosine similarity is 1. For these two angles, for A and C, the angle is 45 degrees, and cosine is square root of 2 divided by 2. So it's like 0.7. Okay. So our idea that we can decompose our matrix into the one which will be a representation of our documents in some latent space. Yeah. So we can find this beautiful representation of documents in latent space with k dimensions, and the projection matrix, which is bringing it back into the world of words. So the other matrix which will, together with this matrix, form our term document matrix back. Okay, and this matrix can be used to project the words into the same latent space. Okay, so let's look how it, if we suppose that we have such a decomposition, what will be the result? So our ranking matrix, also ranking vector, can be obtained by two multiplications. So we have this latent space representation of documents, we have this projection matrix, and we have a query. Yeah, 3 matrices. So if we suppose that we have them, and what's the first observation here? Let's look at the memory. So this matrix, if we think about this matrix, requires 1 billion by 100k of elements, which is 100 trillion of data. So it's like 100, if we store it in floating point values, 400 terabytes of data. 400 terabytes sounds not that big, but you don't want to spend all your hard drive on the indexing 400 terabytes. What about this? You have 1 billion here, you have 100 million here, so it's like 100,000. So it's like around 1 billion of elements multiplied it by k. So if k is, let's say, 300, what you have? You have 300 billion. It means that this is 1.2 terabytes. Not 400 terabytes, but 1.2 terabytes. So significantly smaller. Yeah, so significantly smaller. If you have even less, if you have 100, so it's even small. It's less than a terabyte. It's like 1.4 gigabytes. Oh, sorry, 400 gigabytes. 400 gigabytes. So it will be very good for us if we can find such an approximation for our metrics, term document metrics, with low rank matrices, the smaller. We want them to be exactly the same. Unfortunately, life is hard. So what we can say, we can allow it to be approximately equal. And this is the first observation. So memory consumption, we significantly win in memory. The second thing is that how can we use this? How can we use these matrices? So we want to store the documents in index, and we want to obtain similar documents for the query. If we store this part, so documents in latent space representation, in the index, somewhere on the hard drive, and before running the query in the index, so putting the query in the index, we will multiply this query by the projection matrix, the one which is the second low rank approximation. So we group them together and we run this multiplication, which is pretty small matrix, k by number of words, and multiply it by the query matrix. And of course, you understand that this multiplication requires what? This is a very sparse matrix, yeah, very sparse vector. You have 100,000 of words, but your query is actually like very small. So your task is just to pick some few rows from here and few columns from here, So for example, this and this word will be in the query. So these and these positions in the matrix will be used. So this column and this column will be just used for computing the multiplication. So the computationally inspiration is very inexpensive. So it's like, you can think about this as about embedding model. So the word embedding is used to represent the vector in latent space. So like if you ever heard the word embedding, it means that there is latent space of representation. There are some concepts which lay in this space, and our embedding is a coordinate for an object in this latent space, because it like embeds, it puts the object into the space. That's why embedding. Yeah, so you can think about this as a simple machine learning model. So we apply a machine learning model to the query vector, and then we use these embeddings to search in the index. Okay, very simple. The last thing left is, how do we do this? How do we split the matrix into two parts? And I hope that all of you who know mathematics somehow are already anxious to say, yeah, PCA, SVD, all these words. So I will not hide it from you. So matrix decomposition in linear algebra in some levels, maybe you study it, maybe not. There are ways of decomposing the matrix. How do we decompose them? It can be different. So for LU decomposition, you will find triangle matrices. For QR decomposition, you will find an orthonormal matrix divided by a diagonal matrix. And one of the most beautiful decompositions, which is actually, I think, introduced hundreds of years ago and was popularized in the middle of 1950s, like somewhere here, is SVD, singular value decomposition, which breaks our matrix into three matrices. Orthonormal matrix, so it means that each vector here is orthogonal to any other, and it means that normal means that the norm of this vector is 1. Okay, orthonormal. Another orthonormal matrix, so this one is U, this one is V transposed, actually V Hermitian conjugate, and one diagonal matrix, which is sigma, the matrix of singular values. I was told that in this university, there are three major milestones of education, which is usually explained multiple times. This is Fourier transform, SVD, and conditional probability. So I think that I will not steal your time by explaining how SVD works again. I will only say that SVD is a very good approach to find a decomposition of the matrix with a given property. So property of orthogonality. This is the mathematical basis. Actually, if you think about geometrical representation, SVD breaks our matrix. It thinks about the matrix as about the operator. And you can say that there's three operations. First, you use orthonormal matrix, which is what? A matrix of change in the coordinate system. It uses for rotation. It rotates the data. Second matrix, which is the diagonal matrix with some values. What does it mean? Diagonal matrix is the matrix which rescales the features of the vector. Okay, so it's the matrix of, how to call it, zooming and like changing the ratio of the features, so extending and so on, and one more rotation. So two rotations and squeezing of the geometrical objects. So SVD decomposes your matrix, thinking about the matrix as about the geometrical operation, into three stages: rotate, change the ratio, and rotate again. and again, the geometrical representation. Any other representations are also welcome. So for us, what is important? That the idea of this is to sort, the idea of SVD is also to sort the importance of the dimensions. So this middle matrix holds the what is called the singular values, and these values define the scale of importance. How important is this feature for this data? So we not only define the concepts here, yeah, so the orthogonal representation of our data, but we also say what? We can sort them by this matrix in the order of importance. Importance means what? How well defined is this general tendency in the data? So if your data is all aggregated on the far end of the x-axis, for example, of the first dimension, it will bring the first dimension to the most important one. So the data observe this dimension as very important. So all the values in the first dimension are important. So it will bring this dimension into the top and sort these dimensions in the order of decreasing importance. What it gives to us. So this one is the new coordinate system, new orthogonal representation for the data. And this one is importance, okay? And if we group them together, we will find as this is what? Orthonormal multiplied by a diagonal matrix, this will be orthogonal matrix, okay? Orthogonal matrix, which can be for us used as the first one. So this one, if you look here, so let's look at the dimension. So our matrix TDM has what? TDM transposed. So here are a number of what? Words, documents. So I usually confuse them. So let's say here, documents and words. Oh, sorry. Documents, and here we have words. Okay, so it means the decomposition will be of the following size: number of documents. Let's look at the non-reduced version. Number of documents for this matrix. Number of documents by number of words, and number of words by number of words. So this matrix is square words by words. This matrix is square documents by documents, and this is diagonal matrix of rectangular form. So it can be. So it's zeros, and there is a diagonal which stops in the shortest part. And we know that this matrix actually manages the importance. So the further you go by this diagonal, the less important are the components of the matrix. And after doing this, we can reduce the number of dimensions of latent space by cropping this importance matrix. So, and we say let's importance matrix will be R by R. So we will use this rank R. So we assume that 300 dimensions is enough for us. Okay, then we will have the matrix number of documents by R, and this matrix R by number of words. Okay, so documents by R, R by R, and R by words. Okay, the sizes of matrices. Yeah, the question.
What is R?
R is our rank which we will use for approximation. We can somehow find it if we can for the data, but the nature of data is to be noisy. So data is noisy. It will, with a high chance, if you exactly will compute the rank of the matrix by some known procedures, you will end up with the rank equals to the size of the matrix. Like it will be the number of words, for example. And this is what you don't want to. What you want to is to have pretty good approximation. Yeah, you understand? So pretty good. It means that if you subtract an approximation from the original matrix, it will be almost zeros, almost everyone. Yeah, so the good approximation. When you do TDM, let's say, term document, term document I'm term document matrix approximated minus term document matrix, it will be almost equal to 0. Yeah, so 0 matrix, almost. And this is the idea of approximation. So you approximate in some sense. So what is the possible way of this almost equal? How can you define almost equal for matrices? What's matrix is almost equal to 0? Is there any metric for a matrix? So is there any norm for a matrix defined? Yeah. Determinant is not a norm because it can be negative. But you're close. Guys. Matrix norm. Matrix norm. Okay. So let's see. So this is the definition of a norm. What should be the norm? Any well-known norms for you? Supremum. Do you know this one? This is a generalization for actual vector norm. And this one you should study. The L2 norm for matrices. Frobenius norm. Just sum up the squares of the elements. Never heard it. I'm sorry. So you should know there's Frobenius norm. So this is the way you use for example, for bringing the regularization to neural networks. So if you have the distance, you compute the Frobenius norm and you want to use it for finding the error. So Frobenius norm is just a generalization for a vector norm, just for matrices. Okay. Control F5. I think it will not work for me. Okay. Okay, so there is a norm. There is a thing which can say that this matrix, like TDM minus TDM approximate, equals to 0, meaning that the Frobenius norm of this matrix is almost equal to 0. Okay, this is how we can measure it. Okay, so sorry guys, I see that I used 10 minutes of your break. So if you don't mind, I can stop here and continue on the next lecture, and we'll have a 10 minutes break. Or I can continue and finish right now.
There are 2 slides left.
2 slides left. So I continue and we will have a break after this. Perfect. So as I said, SVD breaks our matrix into 2 parts. This one will be used for representing our documents into the latent space. And this one will be used for as a model for projecting the query vectors into the latent space. Great, so we know how to do this. Is there anything which is very similar? Principal component analysis. You all heard about this. This is the thing with a very similar idea. And for a long time, I was confusing these approaches for working with vectors. But there is a very significant note I want to give you. Yes, PCA takes the data which can be possibly correlated and forms a set of linearly independent values. Perfect. Second, this sorts principal components from the largest possible variance to the lowest one. So again, the same, the importance is sorted. What is the difference? PCA can even be implemented with SVD. So it means that SVD is the core of PCA. You can run principal component analysis with SVD. The only thing here is what? Is that it changes the centering of the data. If you run SVD, you want to preserve cosine similarity. Cosine similarity is preserved when you do SVD. And the angle between these 2 points, A and B, will be that alpha prime here. But for PCA, first step you do, you subtract the average and you change the cosine here. So what you preserve the variance in the data. But in PCA, you don't preserve cosine similarity. It's very simple to see that the points which, like if you do PCA, you can change the order of cosine similarities of points. So it means that the ranking of documents in the original space will be mixed in the transformed space. It means that applying PCA to such a data is not a good case when the data is not centered. And in our case, as all the values in the dimensions, they are positive, it's obvious that the data will be not having the origin of 0. It will have the origin of somewhere here. You can use some tweaks to overcome this. For example, if you take all the data and add it to the data set with minus sign. So then you will center the data and you will run PCA on this data. But this is a tweak, and it doubles the size of the data. Yeah. But here I want just to warn you that even if these methods are very highly correlated, if they go together, it means that SVD here for this particular data is more is a better choice because of the idea of cosine similarity. Cosine similarity is preserved by SVD applied to a positive valued matrix, where principal component analysis will change the metric. It will influence the cosine similarity. Okay, and this is an example of applying PCA to nutrition data. Just showing you, like, sorry, this example was for Russian book. So the stars and all this stuff means different types of food, and you see that actually on the graph. For example, sweet things cluster together with grains. Yeah, so because they have a lot of sugar in the content, that fruits are grouped together with vegetables. Crosses and circles, they group together because they have similar nutrition. So we took this high dimensional representation of, I think, 17 dimensions in this lab and brought it into two-dimensional representation, and it remained the principal component. Principal means that it found some orthogonal features which are the best in representing the variance of our data. And you still be able to find some glance of information here, some important observations about the data, even having just two principal components out of 17. Okay, so this is the way how PCA is usually used, to reduce the number of dimensions for representing the data on the graph. Let's go through the lecture once again briefly. So vector space is a concept which says that we can define vectors for our text and words to represent them in some unknown latent space. But we know that TDM is sparse. That's why we have problems with computations. And the concepts are non-orthogonal by now in TDM because they are words and the words correlate. Distributional hypothesis gives us an insight. The words correlate and the distribution defines semantics. Latent space analysis says, great, I know that we should search for low-rank approximation, and this approximation can be obtained by SVD, singular value decomposition. So these are, like, from vector space, the most general idea. Distributional hypothesis gives us idea that correlation and semantics, they actually strongly connected. Latent space analysis shows that we can use this to obtain orthogonal concepts, and SVD shows how do we obtain orthogonal concepts. These are the steps for building embeddings for text and words. Reading is here, links in presentation. We meet at 11:05. Okay.
Okay, thank you.
Okay, guys, I hope you had some sugar and then you restored your brain power, because we need some more of your computational power in the second lecture. Before we start, I forgot completely to do a very annoying operation, which is called attendance check. So Avais is here. Ayumide, I saw you in the chat. Kirill здесь. Eder Queen. Let me see. You're at least in the chat. Eder Queen, are you here? Denis Fokin. Khadija just left. Okay, I saw her and she left. Roman Garaev. Vaigu. Ikram here. Firas here. Елизавета туточки. Daler. No Daler. Ярослав вижу, слышу. Герман был, да? Герман в углу сидел. Айдар тоже здесь, да? Да. И Данил. Шихин, это программист этот, да? Его сегодня нет. Окей. And the only person who I didn't mark is Daler. He was in the very beginning, and I don't see him right now. Queen, yeah, I marked you as present. So Daler, but I saw him. Let's be kind and say he was in the first lecture. Okay. Attendance saved. Yeah, everyone is here, so I remember who joined in the very beginning. So let's be fast. We have only 1 hour left. I don't want you to take your time of lunch. I know that some students can just run away for lunch without any warning. We just went through the long way of mostly linear algebra and some hypothetical ideas, distributive hypothesis and vector space model. And these two hypotheses, it's Latin, they all gave us the chance to apply to the just the matrix, which is rectangular collection of numbers, some beautiful mathematical operation like singular value decomposition, to at least approximate the latent space, some space with the only assumption. Assumption is what? This is the linear projection. Yeah. So we did what? We took a matrix, then split it into two, which then by multiplication can go back and form the original one. So it means that both parts of decomposition are linear operators. Yeah. So the operator which projects documents into the latent space is a linear operator. The matrix which projects words into the latent space is a linear operator. This assumption is good enough, but no one said that it will be that easy work. So for practical applications, everything was perfect. Some good results were obtained even in the late 80s. But can we do better? Can we find the better latent space for our documents and for our words with some maybe non-linear approach? And to do, I think that as we didn't have any break, we don't have to refresh these concepts. Term document metrics, but all these things you remember from the previous lecture. So today we speak about what is missing in LSA, latent space analysis, and I will speak, and you will ask if something is non-clear, how to solve embedding task with more complex models, not just decomposition of two matrices, but with some non-linear approach. And of course, here I don't want you to study the machine learning models, but I want you to understand the principles which were put inside. So how to build machine learning model is in your machine learning course. Here we will speak about the ideas which led to these architectures. Okay, the critics for LSA. So LSA stands for latent space analysis, the procedure which is done with SVD. Okay, so which remember. Of course, the speed issue at SVD, if you take the full size SVD, if you want to decompose the metrics into two, it will require significant memory and CPU time. It takes, I don't remember how many memory, but it takes cubic overhead in time. If I'm not mistaken, just a second. I forgot to give myself some notes. If there are some notes, some slides. Yeah. Okay, F11. Okay, you can see. So significant increase of time and increase of memory with the growth of vocabulary, with the growth of document collection. And of course, you can use some tricks to fight with this. For example, you can compute the reduced form of approximation without the full form and then reducing it. So you can run your computation in the way it produces the reduced form only. You can run fast randomized SVD, which is proposal by Facebook. The paper is here. You can use any other decomposition approaches which split your metrics into orthonormal and orthogonal metrics, like ALS, alternating least squares. And both the first and the second, they suggest distributed and stream inversions. This is very important. So if we usually do any lab in our university, we take a laptop, we run Jupyter Notebook, or we take the Google Colab, and we run some decomposition or some machine learning model in this environment. But as I mentioned, just imagine the size of the data set. If you have billion of documents, the amount of RAM on a single machine can be not enough to even store all the data. And it means that you need to either do some streaming, means what? You read the data from hard drive, put them into RAM, and then process, and then you unload the data and replace it with the other from the hard drive. So you stream the data through the model. You don't store all the data in RAM, you just store the parts. And distributed means what? You can try to benefit from multiple machines. You have the cluster of computers connected by the network, and you train this part here, and these methods allow us to do this. But still, CPU time and memory, they don't decrease, but you just distribute this time or you distribute this memory. The second issue with LSA, with the approach which requires SVD, is that PCA and methods like this, they assumes normal distribution of data. For PCA, you want to minimize the variance, and you assume that the first principal component is taking the direction in which the variance of the data is maximized, and you first do centering in PCA. Yeah, what's interesting in PCA? PCA takes the center of the data and then estimate the variance. And what does that mean? When we put the center into 0 and we estimate the variance, we think about the data as about normally distributed. So we define the distribution by mean and variance. And this is the idea of normal distribution. Other distributions can have, for example, shifts. So for Poisson distribution or any other distribution which is more general for the words. And you remember that we discussed in the previous lecture that the words in language actually they have what? They have logarithmic like distribution, so they decrease. And no one said that the distribution of data will be normal. This is not set in stone. And PCA has this assumption, and that means that there should be some methods which can allow you to use different hypothesis about the data, a different idea. For example, PLSA, it's the extension for LSA, which allows you to use different distributions, not only normal, but others in your data. It's called multinomial distribution. And this is very hard to think about any method like LSA, PLSA, when we just imagine when you add a new text or you add a new word. So you know that for a sparse matrix decomposition is very unstable. So you change, I have a nice demo, maybe if you want, I will share with you this notebook with a demo how the changing of a single cell in a sparse matrix can significantly influence PCA results. And I will definitely share it with you in the chat after the lecture, just remind me. So this for sparse matrix, decomposition is unstable. Adding new text or adding new word can just significantly disturb the things, and you need to recompute the representation. And that's the problem with this method. So SVD is doing this done once, and you can just fine tune it. So some models have so many assumptions about the things. And can we just be like normal engineers? Can we be just like, people who don't care about statistics and mathematics, which is hard to think about? And we just say, let's take some complex thing and let's plug the data and get the result from there without even worrying about what's the nature. Let's bring some nonlinearity in this thing. Let's make it complex and let the model decide what is the distribution, how to work in case we get the new word or get the new text. Is it possible? And today we know the answer. Yeah, you're here to study data science and you're very fond of machine learning. That's why you came here. So machine learning became like the key to the new world of latent space retrieval. And the first, as I can say, the first important milestone in this way of bringing contemporary machine learning methods like neural networks mainly into latent space analysis was Word2Vec publication. It was done in I don't know, when I was joining university, it was just 2 years ago. For now, it's very ancient times ago. So 8 years ago, this paper was written, published, I think, written earlier. And the idea was very beautiful. Let's try just a simple neural network to do this. And you will see that initially the architecture of this network was not that far from just matrix decomposition, but it brings very interesting and brilliant results. And by nature, letting neural networks into this world, by nature, we allow those things which were addressed by stochastic SVD or alternating least squares. We allowed this procedure of obtaining latent space be both distributed, because we can train neural networks distributedly, and streaming, because we can use stochastic gradient descent. You understand the difference? So for gradient descent, you need to run all the data, compute all the errors, and propagate the result. For stochastic gradient descent, you just load the batch, you run the batch, and you fix the error for the batch. So you just can choose the size of the batch as big as possible for your machine and keep the data in RAM and just stream the data through your model on a single machine. So by nature, neural networks allow you to use streaming and distribution. That's very good. Second, Word2Vec is not just a single model, it's a collection of models, and we will consider both of them. Yeah, so some comments which I already mentioned. So what is inside? Inside there are two approaches, skipgrams and continuous bag of words. What are the ideas behind? We will expand them later. For skipgrams, it means that we have the context, the short context, short sequence of words in the sentence, fixed size. So in this case, it's 5. And we will predict the context by the word. So having the word, we try to see which words are highly probable, the neighbors of this word, which will occur. So having the word fox, we more oftenly in our practice will need quick, brown, jump, over, and less frequently, for example, we will use see the word dinosaur or coffee or I don't know, singular value decomposition. They usually don't appear together in the context. So this is natural application of distributional hypothesis. The context and the word connection. And the continuous bag of words is actually doing the opposite operation. It predicts the word given a context. Yeah. Bag of words, you know this. Continuous, you know this. And by knowing the context, you can easily predict that there should be an elephant, a hippo, or giraffe, so with the highest probability, and with less probability there will be an ant or singular value decomposition. So these two words are improbable in my example with safari in Africa. Okay, so let's go deeper. Continuous bag of words. I used this term multiple times, but I want again to emphasize that bag of words is a approach which represents some real world object. It can be a sentence, a person, whatever, with a multiset. Multiset means we don't care about the order, we care about the count. Okay. It doesn't mean that bag of words is just the thing which can be used for words. Actually, it was introduced for words because it's bag of words. Yeah, but bag of words technique is used, for example, in image retrieval when we speak about clustering sift vectors. So word can be different concepts. So if you replace word with something which is discrete, bag of something can be used in music, in image retrieval, and so on, so on, so on, so on. Okay, continuous means what? So this bag of words is a continuous block of your text without gaps, 5 words, and then you move with this sliding window through your sentence. So 5 words, then shift by 1 word, 5 words, shift 5 words, and so on. Okay, how do we train this model and what's the architecture here? The input of the network, we already are familiar with such kind of vectors. It's the vector of the size of the dictionary. Okay, so our dictionary, assume in our case 100,000 as in previous case. What we do here, we encode the context with a technique which is called one-hot encoding. It's not actually one hot because it's not one. It's the one-hot encoding is in Russian. Don't have this even term for this, but the idea is that one-hot means if you have a discrete set of discrete objects, you give a number to each object, and you identify object with 1 in the position for the object. So this is, if you have 5 different objects, you will reserve 5 places in the vector. And if we want to describe the object 1, we will put 1 in the position of 1 and zeros in the other positions. If you want to describe the object 3, we'll put in the position 3 and others will be empty. So it's one-hot encoding. So 1 appears in some place and represent the object. We slightly generalize this idea and we encode the context. Context is, you remember, it's some small number of words. Let's say 1, 2, 3, 4. Quick brown jumps over these 4 words. That means that we will put 4 ones in the vector of 100,000 positions. Okay, so we encoded the input. The output is what? Again, the same size, but here we put 1 in the position of our word, which we want to predict by context. Great. What's the idea behind that? Activation models likelihood of observing the word given a context. So it's like a probability idea. So it's not just cosine similarity or something, it's the idea of probability. We here speak in terms of probabilities, and we are building the model which predicts probabilities. And here is the architecture of the network. So who can say, where can I, from this network, grab my embeddings, low dimensional representation of the text? Excuse me? Hidden layer. So yeah, if we split this architecture, what does it mean for us to apply the neural network? So we take the vector of some context, and we want by this context predict the word. This is what our network does. First, we apply the layer here, this layer. Okay, first input layer. It's a matrix multiplication plus what? Plus some nonlinearity. So yeah, this is the first layer of neural network. Okay, and then we do the same here. So it's again matrix multiplication. I just omit the bias. We add the bias somewhere and do some nonlinearity. And yes, you see that this is very similar to what was done actually by initial thing. But here we only added nonlinearity. So for LSA, there were only matrix multiplications. Here we add some nonlinearity, which makes our model more powerful. Yeah, so these sigmoids, they are giving significant power to our model because it allows us to model very complex transformations. Previously, it were only nonlinear things, also linear things. Now they are nonlinear. But the idea is the same. So this matrix projects latent space into words, and this projects context into latent space. Okay, two matrices. Multiplication plus sigmoid brings your context into latent space, and then you transform it back. The same as it was in the previous example. So the network here is very shallow. It borrows almost the same idea, but it adds nonlinearity, which becomes a very powerful tweak for the original model, adding nonlinearity. Okay, the second approach is opposite. So we put the word and we predict the context. And the original paper says instead of predicting the current word based on the context, we try to maximize prediction, classification of word based on word in the same sentence. So we look at the word and we try to see what are the highly probable neighbors for this word in the context. It will give us what? In the output, it will give us a distribution of the most probable context and decrease into the least probable context. So you put the one hot encoded word as an input, and you have the distribution of probabilities as an output. And you pick those which are maximum to predict the context. Okay? And they observe the following. So increasing the range improves the quality, whereas it increases the computational complexity, obviously, because you need more computations for more data. And they also found that it's a good idea to encode words differently depending on the distance in the sentence. So the further are the words, the smaller will be the signal of the target here. So we will put less weight to distant words and more weight to close words. So the context will be not uniform, but it will be decreasing with the distance. So few ideas which gave a good results for the paper. Data in input is the same data in output. Not sure that I understand the question. The dimensionality of data is the same. The models are working in the following way: that the first model, continuous bag of words, takes the encoded context and predicts the word, whereas the continuous skipgrams take the word and predicts the context. So the dimensionality is the same, but the structure of the input and output is different. So the semantics behind. So these are the ideas. What can we say about these ideas? So one of the interesting positive observations was that with this paper, the vector space arithmetics appeared. So we cannot say that this was just, it appeared just here. Maybe you can observe some similar effects in just LSA, but the idea was the following. It appeared that not only the data items like words can have the good distribution when the similar words are laying together in the same latent space and non-similar words are very distant in this space, but also that the relation between words are defined by similar vectors. So you remember that the metric space is about distances and vector space is about operations of adding and subtracting vectors multiplying by scalars. And what was observed that two types of relations, syntactic and semantic, found the arithmetic projection in this space. What does it mean? So if you take the word queen and subtract the vector for a word woman, so this will encode the relation between like the royal person, yeah. So the queen and woman is just a royal person of a female kind, yeah. And then you add man here instead of woman. So you subtract woman and you add man. The closest vector which you will obtain will be king. So it means that these two relations, queen and woman, semantic relation, and king and man, they are almost the same vectors. They are very similar vectors here. And this is semantic relation. The same can be for capitals. So Paris in France, London in England, they have the distance of very similar vectors. This is a semantic connection and also syntactic connection. Obvious thing here is like this, multiple forms and the comparative forms like slow with the slowest. They are always, not always, but they're there's a high chance that they have the similar vectors representing these relations. So this arithmetics was just a bonus because the task was what? Was the similarity, but we also obtained arithmetics which was not meant to be here. Is it true? I'm asking the paper. I can say that this is a trick. Why? So yeah, they say that we wanted good embeddings, but we also obtained arithmetics. But actually, let's look at the paper and the task. So first of all, look here again, just to be able to reproduce the paper, some information about how it was trained. It was trained with stochastic gradient descent, backpropagation, nothing special. Learning rate was this small, and then it was decreased linearly throughout the training process. And actually, all this model was trained on the data sets, which were, first of all, Google inspired. So they all came from the same company. And these data sets were designed to solve the problem of semantic and syntactic questions. So these data sets were initially designed to be able to predict semantic relations between the objects and syntactic relations. So yeah, training was on the text data, but the task of the group of researchers was to predict semantic and syntactic relations. And this is like obvious that they observed the result, which was the actual sense of their target. They optimized their model to solve the problem of syntactic and semantic relations, and they, observed the arithmetics of syntactic and semantic relations. If they trained their model, I don't know, for any other kind of relation, maybe they will find another way of arithmetics, in their latent space. This is the sample of the data set. You see here that there are different types of relations like capitals, currency, city and state, and syntactic relations when you have adverbs, verbs, and so on of the same meaning. And they showed in their paper very high accuracy compared to previous best models. So skipgrams were the best in semantic accuracy and continuous bag of words in syntactic. And what is actually important here yeah, it may be I can say that there is some juggling with the causes and the results. So what was the initial? They wanted to maximize semantic and syntactic quality, or they wanted the good language model. But for this particular task, they broke the 50% barrier. So they were very good in solving these tasks. No matter what was the original reason, the result was impressive. Yeah. So in these tests for semantic and syntactic relation prediction, they were the best at the moment. Yeah, definitely.
These algorithms are trained on English dataset.
Yeah, yeah, originally, yes.
Do you know how it works on Russian dataset, for example?
If you want the numbers, the best way is to open. Let's say so. Just a small step aside. Sorry. I'm not sure that other students, yeah, so other students can see. There is a website called Rus Victorious, and here are different models in different data sets with different models trained. For example, continuous bag of words. Yeah. And there are data sets which used National Corpus of Russian Language and other like Russian News and so on. So we can go here and see different results. So similarity, lexical similarity, and Google analogies. So numbers results for these things. So if you want to see which models are leading here, please go at Rus Victorious. It's the best place to learn about different models applied to Russian language. It's the project very tightly connected to National Corpus of Russian Language. Control F5. Boom. Okay. Yeah, about the problems and almost any other model problems which should be considered. So first, very important thing, these paper didn't bother about out of vocabulary problem. So you fix the vocabulary. You say this is my vocabulary. This vocabulary is derived from the frequency of the texts. Usually, there is a parameter which says that I will take all the words which are occurring in the corpus 5 times or more, and others will be just removed, and there will be no representation for them. And what should we do if in the query, for example, they appear a new word? So how should we work with this? For this word will be just invisible for a model. And when you do search for some rare word, there will be no chance to retrieve a document, any. So just no documents similar, because the vector for you is 0. Today, there are some approaches, and one of the interesting approaches is subword tokenization. For example, some rare words can be some transformations of other rare words, like scientific terms in different sciences can have same stems or same flexions. And if you don't want the word to be in your vocabulary, you can go for subword tokenization, different types. So it can be just 3-gram subword tokenization, or the approach which is used in BERT, in transformers, when the size of the gram can be also different. But there is a chance to split the word into parts and find some kind of embeddings for these subwords. And if you cover all possible subwords in your vocabulary, then you are safe. So you trained at least some embeddings for them. But this problem wasn't addressed in the paper. Second, at that moment, at the Word2Vec paper, they didn't care about grammar, abbreviations, forms, and homographs. So you understand grammar, the words have flexions, abbreviations, they should be expanded. Forms of words, again, some different forms like be, is, are. These are 3 different words. Actually, they're the same. And homographs, like as I mentioned in the previous lecture, for example, just imagine we have Brown beer and Professor Brown. the Brown beer from the capital letter B, and Professor Brown from the capital letter B. In one case, it's the name. In another case, it's the word, or even like more complex stuff like I think in English there should be something like in Russian. I have a lot of examples, like a stream, yeah, stream, or a spring, yeah, spring. Spring is a season. Spring is the like a small river, and so on. Yeah, so there's multiple meanings for the same word with very different actual semantics. And this paper didn't discuss what they do with such words. They can be glued together. Again, training depended on, but we cannot do anything with this. It depends on the context size, obviously, and it depends on the dictionary size. Just you should know that it's a linear dependency on both. And the last important thing here, that in previous method, in OSA, we had the tool to represent both words and texts. Yeah, here we only prepare embeddings for words. And the only thing which this method allowed us to do is to do vector averaging if you want to build an embedding for text, for a sentence. And in my personal experience, I know what will happen if you average a lot of vectors. What's your suggestion? If you take the sentence of 20 words and you average the vectors for these words, what will happen? Yeah, we'll lose most of information. It will move towards the average vector. And if you take two sentences of very different semantics of 20 words and you average any of them, the results will be very similar because they will be just some average vectors with uniform distribution of features. And this is the problem. So the longer the sentence, the more information you lose, and less you can rely on cosine similarity for retrieving the documents. What can we do to be able to retrieve the embedding for a text? And the idea came from the same authors, I think 2 years or 1 year later. And the model was later called doc2vec, document to vector. And originally it was called paragraph vectors. The key concept there was that they introduced the new entity in this training process. And they say, yes, there will be still the vectors for words. So the embeddings for words, we will keep them in the model. But also, we know that each document, that's called paragraph, has its own meaning, and they are different. And this meaning, of course, depends on words. And we will also derive during the training process the embeddings for paragraphs. So we will do what? We will take the data set, we will assign to each paragraph a number. And let's say this number will be another fictional word. And we will do what? We will concatenate this word to any context we will use for training. So we used context. We take this the same like word2vec procedure. We take the context and we predict. In this case, they predicted the next word. So their context was like A, B, C, and they predicted the next word by the context, not the internal, but the next one. But also they invisibly concatenate this word paragraph to each of these windows. So they add it like this. They take the words. For each word, they have the vector. They prepare the vector for context. And then they do what? They concatenate the vector of paragraph, which they train, to any context, any set. So this is like the combination. This vector is a combination of the paragraph representation and the words representation. Okay, and what they do they obtain in the end, they obtain two important matrices. The important matrices are matrix D, which has the size of dimensionality of paragraph vector, let's say 100, and the number of paragraphs. So matrix D, and the matrix W, which is the matrix of word embeddings. So the number of words and the number of dimensions for the word, the same as in the previous method. Okay, And their idea is to, again, so they take this paragraph vector and they bring it to each context. So that means that as this vector is different for any paragraph, the words weights are shared among all the texts, but the embeddings of paragraphs will be different. So if we, for example, do a forward run of the network, so after training process, we did a forward run. What will happen? We take the vectors of words, which we know. We take the vector of paragraph, and this vector of paragraph will influence the prediction. So in one paragraph, it will predict one word. In the other paragraph, it will predict the other word. For example, one text is about United States, one text is about Russia. And here are the words, the president of, yeah? And this paragraph vector will lead to predicting Russia, and other vector will lead to predicting USA. So that's how they brought this idea. They splitted the semantics of paragraphs and semantics of words. So words are trained separately, but paragraphs also trained during this process. The only problem is that how to inference the vector for a new unseen paragraph. Yes, we obtain the weights, the vectors for seen paragraphs. So those are which in the data set. But what will we do if we have the text which was previously unseen? How can we do this? And they said, in this stage, in inference stage, we fix this W, means that we don't change the weight of words. We fix this. These are the parameters of softmax function. So these are just bias and weights of softmax. And we do gradient descent on D. So we, let's say, train our model, the new vector. We predict the new vector, we tune the parameters in the way it minimizes the loss for this particular paragraph. So the embedding of this paragraph will be retrieved by a short gradient descent procedure. So that's the idea. So this inference requires some additional machine learning training, which is in practice very fast. So we will observe it in your homework that retrieving a vector for unseen paragraph is a pretty fast procedure, even if it's like, again, training the model. But as the major part of numbers is fixed, you need to do some very small training here. Again, as in the previous work, they had two models of training. One is distributed memory. So they concatenate paragraph and word vectors, and they predict the next word. And distributed bag of words, they ignore the context words, and they force model to predict words randomly sampled from a paragraph. So they train the paragraph vector in the way it, in the best way, predicts the words in this paragraph. So you understand? So this vector is trained just to, you take the paragraph, you take some window of a paragraph, and you randomly sample some words. And this is the data set, the paragraph ID as an input, and the randomly sampled words as an output. And you train the model to predict them. These are two approaches of training doc2vec model. Again, what about training this model? They use stochastic gradient descent. This still requires running some additional training to retrieve the new vector. The task changed. So you understand that whatever you obtain is good for a particular task. So embedding for any text is not just a perfect representation in the vector space. It also represents the task which you solve. Yeah. In the first task, the latent arithmetics appeared because of the task of predicting semantics and semantic and syntactic relations. This model was initially trained for the task of sentiment analysis. So they trained the model, but their result was actually to maximize the problem of sentiment analysis, to predict the mood of the text. And they used these embeddings in the classifier of mood. And actually, I think this was the reason for another. That is why they added punctuation to their tokens. So previously they just used only words, but if you want to predict the mood, of course, exclamation marks, punctuation can be very important in predicting the mood. So that's why they added punctuation and treated them as normal words in this model. So I think the final task, significantly influenced the approach they used. So these are two models, and now we are equipped with a nonlinear model, which can bring us the vectors in some latent space. Computation is again almost the same, multiplication by a matrix plus nonlinearity, more or less good for now. So what can we do even better? Yeah. So we are here in the class of information retrieval, and what we saw here that the models here were trained to do some random tasks not related with information retrieval, predict some similarity and something else. Oh, okay. Some more models if you want to read about them. What about going deeper and actually solving the problem of information retrieval? And in 2015, Microsoft proposed the model, which is called DSSM, which they used in Bing search engine, and Yandex adopted this model and significantly reworked for Yandex. And it was used in Yandex, I think, from 2016 to 2020 until it was replaced by transformers. So I think that Yandex is now moving to transformers. But DSSM is the model which was originally designed for a search task. So we are living in the world of information retrieval. It's very good if we can train the deep model for the task of information retrieval. Why not? So what were the observations of Microsoft which they included into the model? First, they trained the model to predict cosine similarity. Wow, that's great. So they wanted actually to predict cosine similarity between what? The query and the header of the document which they retrieve. Header means some text snippet which is displayed to a user. Okay, much better. Before we just did some context prediction. Now we are targeting exact search problem, predicting a good match between the query and the document. They, instead of using words, switched to letter trigrams. I cannot say what was the motivation, but one of the obvious motivation was that typos, misspellings, and so on can be the often guests in search. So why not to switch to the model, which will be like more robust to typos, to misspellings, and so on. And they use only trigrams. So what's trigram? Trigram is 3 consequent letters of the word, and the word is split into overlapping trigrams. So as I mentioned previously, the word border will be split into bor, ord, RDE, EDER. So this is R, border. So the word border falls into four different trigrams. Okay, and the idea is the same. You take the vector of the size of number of trigrams, and you encode the query in this vector. Important thing, this was created for search, and some problems. If we take the Russian language, 33 letters, English language, 26 letters, 26 in power of 3 is less than 10,000. For deep model, this dimensionality of vector is pretty small. Yeah, so like initially we trained word to vector, the shell network, on the data of tens and hundreds of thousands of input values. And now we use deep model, but the size of the vector, input vector, is smaller now. 33 in power of 3 is around 10,000. Oh, sorry, 30,000 of different tokens. So it's pretty small numbers. And some interesting things about training. So what they did, as it appeared wrong, was that the signal, the training information, they retrieved from the clickstream Do you know what's clickstream? The information about how users interact with the websites. Oh, they did what? They assume that the positive result, so the cosine similarity 1, comes when user types the query, sees the document, and clicks the header. Okay, it was like just definite idea of relevance. So the document is relevant, and if user didn't click the document is irrelevant. So you understand that, first of all, clicking the document doesn't necessarily mean relevance. It can be just porn or kitties, and you just click because it's a clickbait. So you just want to click this, and this has no common with the original information need. And second, what if there were 3 relevant documents? You clicked one, and 2 unrelevant documents were assumed as non-relevant. And that's why later Yandex reworked the model. So based on DSSM, the original DSSM, they added some improvements. First, they extended the input layer. Instead of using just 3 grams, they added 1 million of words, of most frequent words of Russian language. And they added 1 million of word bigrams, so the words which occur together. And this together was like 2 million of input values, much better, much bigger input layer. Yeah.
Why small layer? Why is small size of layer?
I cannot say this is a problem, but having the small dimensionality of input vector, as we just discussed, keeping you less space for expressing the information. So just by 3 grams, by a bag of 3 grams, you lose the order. Yeah, so you put 3 grams, and there can be multiple different phrases which lead to the same 3 grams. So you start gluing together semantics of very different queries into the same vector, input vector. If you add additional information like words themselves, you will bring the notion of order of these 3 grams. So you will show to the model that these 3 grams are arranged in these words. Okay, and this is important information. So it can distinguish the same bags of 3 grams, but are originated from different words. So they extended the input size, and they observed interesting things. So first, I mentioned that just doing observing the good document as the clicked document versus all other unclicked brings not very good quality. And they wanted to tune this training procedure, and they wanted to do the following. So they wanted not to bring all these documents which are unclicked to the training set as zeros, but some random negative documents. So not those which were retrieved and shown, because they are highly probably they are relevant, but just some random documents, random sampling. This didn't bring significant quality improvement. Then they decided that they want to do a fake negative example. So they started generating fake things, and they observed the interesting result. The model is that deep. It's enough of this model to learn the style of Yandex developers of faking the headers. So it learned not the fact that the document is irrelevant, but the fact that this document is faked by designers. And what actually helped them was hard negative mining, the technique which shares the same idea as GAN. So GAN is like it appeared later, but generative adversarial networks, when the 2 networks which fight together, one is learning to fake, another is learning to distinguish. Here it was, they have the prediction round, and then they take random best predictions and then put them into the negative samples and the next stage. And then they train again, they have the new ranking, and then they take those which are the best as ones, and those which are randomly sampled from best predictions, as negative. So they tried their model to be as selective for the best ones as possible. And this worked, this one worked. And also very important observation from Yandex, that clicking the document doesn't mean that the document is relevant. And they switched the target. They switched to dwell time. Dwell time is the time you spend looking at the page. So if you click the document, you stay on the page and you return back. If you return fastly in 2 seconds, means that you looked at the document and you understand this is irrelevant to your information. And that means that dwell time can be used to distinguish documents which caught your attention and documents which were not interesting for you. And this is better than just assessing the clicks. Okay? So few ideas from Yandex which were important to building another search. And this resulted in the fact that in 2000, I joined company in 2017. And in the autumn of 2017, it was like the official launch of switching the search engine from inverted index to DSSM embeddings. So what does it mean? That original search phase, what was the base level of search for papers, for articles on the internet, was by 2017 in both Google and Yandex, based on some significant improvements of inverted index, which we studied previously. And only in 2017, Yandex and then Google switched to, that's called a neural network search. So the one which embedded the queries with a model, embedded the text with a model, and used the index based on these vectors rather than the lexems of the text. So it's like a very fresh history. It happened only 4 years ago, even less. And for now, the idea preserves the same, but the models are evolving. For now, Yandex transformers are used for embedding the documents. I just put the paper about Yandex transformers into my bookmarks, but I didn't read it, so I cannot share it. So maybe I will share the paper with you also. And remind me what I suggested to you to share. Oh yeah, the example of instability of SVD. Okay, 5 minutes left. Well, no, 15 minutes left, sorry. Not that bad. Then I'm safe, only a few slides left here. And today, I don't know what I want to say here. You all know what is this. Few ideas behind, so not about the structure, but about the ideas. The idea of creating this model was not to predict the search, not to predict the similarity. The original idea of authors was to build such a language model, that's important, the model of language, without respect to the task which will be solved by this model. And then try to apply it to multiple various tasks of language and to see whether it can overperform existing models. And this helped. So actually, maybe just because the architecture was very deep and very complex, but transformers brought significant improvement in solving multiple problems of NLP. There are 2 modes of training. You know it better than me. And actually, I want you to see that even if this statement, is from the original paper, and they say that the major limitation of standard language models, that they are unidirectional. And we remember this from Dr. Vec. Dr. Vec predicted the next word in the sentence based on the previous context. The word-to-vec idea was to predict the internal word of the context. It was bidirectional. So it was not that all the models are actually unidirectional. Yeah, majority of them were predicting the word. Next word, the one which you use in your smartphone to predict the next word, is unidirectional, predicts the next word. But the idea is not that fresh. It's not only in from the paper Transformers All You Need from 2018. It predicted the masked words, so the idea was the following. So we hide some words, and we predicted by the other sentence. So what can be missing in the sentence? Instead of one word, it's now 15% of must words. And the question, addition your question, transformers are trained to work with pair of sentences to predict these logical connections, which can catch the idea of pronoun. So the pronoun can be linked with the noun of the previous sentence if there is a semantic connection. Like the idea which was in the creation of transformers. Okay, I think we're very close to the end. If you want to cover something related to details of implementation of the networks, please go to the original articles. It's very always very interesting to start reading scientific papers. I don't know whether you did it previously, but for me, it was very good to observe good paper. So like sometimes the scientific paper can be very complex and it's very hard to understand. What I can say that the papers about Word2Vec and Doc2Vec, they're written in the very good language, and it was a pleasure for me to read them. So you can read and understand the method. It's not always happening to machine learning problems and machine learning papers. Sometimes there is a big formula covering the half of the paper, and you just what did they mean? And that guys just discuss the ideas and put the very good examples. So please address the papers if you want to go deeper. I think this is the last slide. So we are even 10 minutes earlier. If you have any questions regarding to the content about the future, please ask. I will be happy to answer. Again, just to remind, today you will have a chance to discuss with Anastasia, and I will come here and be the part of the discussion, what to do with deadlines. So if you want to somehow influence the time and the day, there will be a possibility. Please pay attention to today's lab, see how it differs from previous. I think it's much easier. Maybe your observation will be different, so we can again discuss this. And any questions are welcome anytime in my email. So please don't hesitate to write, because like what I see here is that Nastya is covering the majority of your concerns with the course, with the content, and you say it's hard, but there are no such cases. There are only some cases which are that hard that Nastya comes to me with the questions. So it means that all in all, in general, even if you say that the course is hard, you do a very good job. All of you, like guys online, guys offline, you can solve homeworks. You can do that. Sometimes you fail. That's normal. That's education. It cannot be that everyone gets A. It can be, but it will be an easy walk. So I need you to pay some, time and some blood and sweat in this topic. And as I explained yesterday to Ikram, that my task is to give as much as possible through the knowledge and through the hands-on experience, because this will be your competitive advantage when you will go to Facebook and they will ask you about turn document metrics. They will ask you about the neural network models. They will ask you about cosine similarity, about parsing web pages. And what will you say? Maybe you'll be accepted, but your position and your initial conditions in any company in the world after you graduate will depend on your ranking among others. So if you don't compete with the best universities in terms of the content which I share with you, you will not compete for the positions. So you will stay in Innopolis forever. Maybe as TAs for the courses. If you want like the best life in future, you should learn hard, and you will continue doing this for the whole life. There's a comment online. The course is easy, but the time is not sufficient. As you said, that this course takes 1 semester, but we are studying in block. But you have less courses. You have less courses. So I had the comment that students of previous year said that your homeworks are twice as big as theirs. That's because you have 7 homeworks and they had 14 homeworks, but you have only 3 courses or 2 courses. I don't know how many. 4 courses. I mean that in this block. And 1 in the second. What I can say.
I have a comment regarding assignments.
Yeah, comment regarding assignments. Go on.
So in assignments, you have put some checks that we need to pass those asserts
Uh-huh.
To check the quality of the code. If you pass those asserts, so our work is done. This is what required from you. So if you put some check on us that this thing needed to be done, but those are not mentioned in the assets. So how can we know that this part needs to be done if those are not in the assets? And we are like graded on the basis of things we are not given.
So you say the following. So there is the
This is
there is a software which you create, and what I can do, I can just guide you with some asserts to check that you're on the right way.
yeah.
And there is a task to solve, like create a crawler, write the composition, implement this, and of course you are not school children. You are not first-year students. You understand that if the task is saying do this, you don't have to pass the minimal possible requirement, just pass the assert, but you need to complete the task.
But you see,
And if you complete the task, you're great. If you just try to pass the asserts, or if you change the asserts, it means that you're not trying to solve the problem. You're optimizing your behavior to asserts.
but-
So, yeah.
Sorry for interrupting. So there are some requirements. You're a software engineer, I guess. First to collect the requirements, and then we work on those requirements. So we have given a document that we need to perform these tasks. So you have given us a document that we need to perform.
And
these
the
tasks.
requirement is in text, not in asserts.
But why are there asserts if it is in the?
The asserts is for self-checking.
But it's for self-checking. We are satisfied that maybe this thing is required by this code. Well, I write some code I don't even understand. I just do it because it is a requirement by you. It is required for getting good grades. It is required to pass this course.
What's wrong with asserts? I don't understand. So you dislike them, or you want more?
I want more because those are not comprised. If even
So you say the following. So I need to write the code, and then I need to prepare the asserts, which will be uniform for everyone. And what I can say that if you look at the nature of the task, you will see that depending on the details of implementation, you will have different results, and they are all acceptable. And you say that I need to prepare, like, and even the following, last year, I did this, and what I got, that this year, Reuters website changed the format of hyperlinks. Google Slides changed the layout. And I cannot prepare the tests for this current state and expect that they will work. For Reuters, if you share the link and you fix the asserts on the content, just imagine in 2 days, what will happen? They will publish a couple of new materials, and the asserts will be non-working. So what I can do, I can only say that there will be some kind of general assert which guides you, but I cannot put asserts on the exact numbers.
there are asserts on the exact numbers, like you have seen that you have given us an assert for checking this should be the string, and this is output, and this should be the input. Those are checks. Those are not general.
But these checks were for loading data set, that if you load it correctly or not.
Those were for our functions as well. I can show you, like those are specific asserts. Those are not generic. But if specific or not specific enough, what should be the criteria? This is the question.
Like, if you want to discuss criteria, and you know that Anastasia is great in the work, you should discuss criteria with her.
We cannot say anything to her because she will not listen.
Why not? She's a very good listener. So you're afraid of her.
She's listener. She will say, "We'll talk to professor." So we're
But here is like you say general things. You say that
this is a cycle.
no, you say very general things. You should understand that as a student, what we obtained the same problem in discussion with Kram. So she said there are general complaints on the course. And we figured out that actually all these complaints came from the material related to coding in web. It's not about the course is designed badly, it's because that you all, in general, like majority of you, had the very big problems with solving the tasks we related to web. Yeah, and this led to extension of time you spend on this, and you think that the homeworks are actually very big. And this was the not because the course is organized in a bad manner. This is because this particular task was very disturbing, and you made a generalization based on 3 homeworks. Out of 3 homeworks, 1 was very hard, and you, wow, that means that the course is very hard. Yeah, but the next homeworks you didn't see them, so but you expect that everything will repeat. There will be hard tasks related to something like this, and you generalize. Here you say that there is some generalization, that there was some assert which I don't like. And all the asserts, I don't like them. They are not very representative. You ask for something strange, but you should generalize the different thing. Asserts are for your help, and the requirement is in text. The text is the task. The assert is something which helps you to pass the block, which guides you. If you want, you can ignore asserts. And I know that a lot of students do this. They change the assert. They remove asserts from you, from the homeworks, because they can be necessary. But the task is in the task. The task, write this code, and you write the code, and nice to check the code and the outputs, not the asserts. Some of you failed the asserts, but still you did the job. Just take this, that you're grown up. If the professor comes to, like the employer comes to you and says, I need your startup to bring me $1 billion next week, and you do your best, and you bring only $1,000. Is it the bad thing? Usually startup takes money, not bring money. If you in a week can bring $1,000, you're great, even if you didn't fulfill the requirement.
No. Listen. A very simple thing. You are saying that asserts are for specific block, but the way you are giving us code, everything is connected to everything. Even our previous assignments are connected to the new assignment. So if assert is working with this code, it means that our code is good and our whole block is good. And even if we go to the last part of chunk, the last chunk of the code, if its assert is working, it means that our first assert should work too, because both of them are connected.
This is a task for you. Prepare the good example with proofs. Take the homework, which you dislike, where asserts are disturbing you from solving the problem. Prepare this, mark saying that this is incorrect. Please don't do like this again, and this in particular. So you say general words. Asserts are. There are multiple asserts, multiple tasks. Each block consists of 20 tasks, I don't know. Please give me the observation, give me the exact example where you think we did wrong. And I will work with this example and try to fix the future based on your suggestions.
So if it's wrong, what will happen to the previous penalties we are given? Like you're saying that web task is difficult, but it's
what you say is wrong is your assumption. So I only can say that if you show me what disturbed you from solving can be fixed in future.
What about what happened in the past?
What happened in the past you will discuss with Anastasia. Because like
the cycle never ends. We go to Anastasia, she says
this is not a cycle. This is a project. You start in January, you finish in March. There will be no cycle. There will be a grade and you're done. Or maybe it will be retaken, you're done. Or maybe second retake, you're done, and no retakes anymore. No more than two retakes. So I'm not trying to argue with you. Last time you came for an hour and just blew my mind away with your arguments. And today I said, give me an exact example of what is wrong. And you say, what will happen in the past? No, we don't speak about the past. You want to fix the future. You're like giving a feedback on a process, not on a cycle. You said that there is a thing which is wrong in the course. Let's fix it in future for your personal patience, for your personal good. You have 4 more homeworks to do. You can influence them. And you don't want, because you don't want to work, you want to speak.
Well, if I don't want to work, I wouldn't be speaking with you, because if I haven't worked,
no, but you generalize. Instead of generalizing, please bring me the evidence of wrong work, of wrong statement.
Generic thing, you're writing an assert, you're putting a limit on us that we should pass this thing. If we pass this thing, it means that
what is called, do you know what's call to action? Call to action is when you come and you suggest, not complain. If you suggest, you say, I wanted this block to be organized like this, and this will help me. If you do this, perfect. You can take this current homework go through this and say, I think that these asserts are redundant and these asserts are missing. And this is how the homework should be organized, in my opinion. And we can agree or disagree on this. That's call to action.
After what will happen after this?
Then I can change the template for this homework, and for the future homeworks, I will consider your suggestions.
And what the mistakes that have been happened in the previous homework? We are penalized for those things. You are saying that on the first of your, like, you know, it was first class, you said that.
I would like to
you
stop
don't
this
want-
discussion, please.
Okay,
You're
stop.
taking the time of other students. Thank you, guys. It was nice to meet you.
Thank you.
Bye.
Goodbye.